Let's set this up. I'm going to introduce the second speaker. This is Vreča. He's a PhD student from Computer Systems Department at Jožef Stefan Institute, and his main interests are computer architecture, compilers, and also digital design. And today he's going to actually show us, he's trying to share the screen right now, trying to show us the Chisel4ml, actually a demonstration of that, and that is the generating fast implementations of deeply quantized neural networks. And I guess you can start from there.
Okay, can you hear me?
Try Stefan now.
Sorry? Is it better now?
Yeah, I think you can do well. Good.
But not now.
So can we?
Should I hold it? Just?
Yeah, do you want to either hold it or wait?
I don't want to hold it. Yeah. Maybe I should button.
That's fine. Try now.
Okay. Is it okay?
Speak up a little bit.
Speaking louder?
Yes, it's fine, I think.
Okay. So this is my presentation on Chisel4ml. It's like an alternative to HLS4ml, but it's based in Chisel. And if you don't know, I will provide an introduction to Chisel as well. Chisel stands for Constructing Hardware in Scala Embedded Language, and it is a library in Scala that is used for synchronous digital logic design. So it is not HLS. You're not converting Scala to, or arbitrary Scala to hardware, but it is a library with components like registers, muxes, and stuff like that. That you then, when executed, you create like a hardware graph, and it's exported to Verilog. Because you're in Scala, you have some nice things so it's a functional language. It's also based on the JVM, so you have everything from Java you can also use in Scala. It also has object-oriented programming and static types and stuff like that. By the way, if anyone has questions, feel free to interrupt. So this is an example of an FIR filter. So it has 2 delays and 3 multipliers and 2 adders. The Z minus 1 is implemented with the register or something like that. I guess. So this is an implementation of such a design in Chisel. It's pretty similar to Verilog. You extend this special class called module, and then you create the I/O using another special class, and then the registers. How can I do the laser thing? The laser pointer. This one? Yeah, it's not working. Okay. Okay, so never mind. So this function regnext is a function that creates a register. So the input to this function is the input to the register, and the result of the function is the output. So you create 2 registers, and the outputs are called Z1 and Z2, and then you simply compute the thing we saw before. So the output is a combinational circuit. And wait, I have to run this first. So we can visualize this. So this is, we have 2 registers, some multipliers and adders. And it also has an implicit clock and reset. You also can use explicit clocks if you have something like multiple clock domains, but by default, it just gives you an implicit clock. You can also get the Verilog of this. So, sorry. This is pretty unreadable, and it also has things for randomization. This is for verification. And I will also print something else, which is fertile. And this is an intermediate representation for this circuit, and it's used to then generate the Verilog. It's basically kind of like Verilog. So the design I showed before is not really a good use case for Chisel because you can easily write something like this in Verilog. A better use case is to write generators so that you can use the code several times. So to do this, we can put here a coefficient. So this is a sequence or a list of weights or parameters of this FIR filter. And then we can create an input-output interface. We create a vector of registers. And then we have some higher order functions that compute the products and the additions. I will not go into the detail, but it is a similar design to what we had before. And then we can use, like if we use 111, we get pretty much the same filter we did before. But we can also create like a cycle delay filter or, oh, sorry. Oh, I guess that's it. The point is you can reuse the code. And yeah, so I will move on now to artificial neural networks. These are kind of machine learning models that have an input vector x and then a weight vector w. And there's another constant called the bias, which is b. And to compute it, you basically just compute a dot product between the input vector x and the weight vector w. And then you add this bias. And this whole thing together is then called the pre-activation, which is input to a nonlinear activation function f, which then is the output. So generally, these things are defined for real numbers, but in practice, floating point numbers are used. But to implement it on FPGAs, of course, it's better to use integers. So there's techniques based on something called quantization aware training, where you can reduce the number of bits used for parameters and inputs drastically, like even like just a single bit works surprisingly well. And for that, you basically quantize the input vector x and w. There's another parameter called the scaling factor, which requantizes. So after you have these multiplications and additions, you basically get a big, so the size of the numbers increases, also the data size. So you have a scaling factor, which can be power of 2. So you can implement it in FPGAs efficiently. It basically kind of requantizes it. So in Chisel4ml, basically has a kind of a generic implementation of a neuron. And then it combines these neurons in different ways to just generate a neural network. So here, this neuron is parameterized by types. So the input type, the weight type, and the output type. Obviously, the input coefficients or input vector and the weight coefficients. Threshold is the opposite of the bias. And then it's also parameterized by 3 functions. Because Scala is really is a functional language, so functions are first-class citizens. And you can use them as any parameter. Like this implementation is not that important. Just it's a generic implementation that gives you a combinational circuit that works like the quantized neuron. So what kind of functions are inputted? So for the most classic is this normal multiplication. So this is for something called uniform quantization. And then you get this vector and you do a reduction. This is just a special function that does a tree-style reduction. And this is addition with like the growing bits, so you don't lose any data. But as I said, you can also have binary weights. So in that case, the weight is either 1 or -1. So you can replace the multiplier with just a mux that gives you the, like, either the positive or the opposite. At the extreme, there's even binarized quantization. So this is the case where both inputs and weights are binary. And then you can replace it with the XNOR operation, and the addition is replaced by a population count. So this just counts the number of ones in a vector. So this neuron function can then be used to create modules. So this is just a simple module. Can't really see much, but it's basically a combinational circuit of like a neural network layer. And this exact same code can be reused for binarized quantization or any other quantization. Okay, so I will move on to the next part of my presentation. So this is a high-level overview of the software architecture of Chisel4ml. So it has a Python front-end and a Chisel back-end, and the Python front-end basically takes in these descriptions of the quantized models. So there's one from the QKeras library, and there's kind of a standard developing called the QONNX, which is an extension to the standard Open Neural Network Exchange format. And then it transforms this to an internal description called the low bitwidth intermediate representation, or LBIR. And it sends it to the Chisel backend, which generates the circuit. So after that, it returns to the Python frontend kind of like a handle that it can use to simulate like a RTL simulation, to do a RTL simulation from Python using like NumPy arrays. So I will now attempt to train a model from Brevitas. And Brevitas is a library for training quantized models. It's based on PyTorch. So this is a data set for jet tagging. And I will just train a simple model of 4 layers, 4 fully connected layers. But it's just one epoch, so it's basically a terrible model. But it's just for demonstration purposes. But the same model could be used for effective jet tagging. Well, sorry, it's kind of lagging. Okay, so this takes some time. And then I'll also evaluate it once it's done. So again, this will basically get random performance because it's trained terribly. But you could see how this could be used if you train like a proper model. Should have used the GPU.
Maybe I can ask a question while we wait.
Yeah. Does anyone have a question?
So I was curious to understand exactly what the output product will be.
It's a Verilog implementation.
So directly Verilog.
Yeah, so like a highly direct circuit implementation. So it means it's highly parallel.
Okay.
So here are the results. So it's a terrible model, but we can implement it nonetheless. We just export it to this Quantix format that I mentioned before, and we can even visualize it. Sorry. So you can see it has 4 general matrix multiplies, and this is basically a fully connected layer. And if you go further, this is the code. First, we transform it from Quantix to that LBIR, and then we create this Chisel backend server in a jar file, which is what Scala is compiled to. And then we call this generate function, and we are basically done. And in this temporary directory, we have a Verilog file and a virtual file of the neural network. And we also get this circuit handle back, which we can use to do simulation. So now we get all zeros because it's a dummy model, but in essence, we would get whatever the model gets. It's also bit exact. I also have a comparison with Chisel4ml. So this is from a paper we published. So we use Brevitas to generate these QNX models. And then we use Chisel4ml to generate a Verilog and use Vivado to do the synthesis. And with Chisel4ml, we use White's HLS to generate a Verilog and then Vivado again to perform the synthesis. And Chisel4ml is set to the highest parallelization settings because Chisel4ml basically only gives you the highest parallelization settings possible. So we set the Chisel4ml to produce the same kind of circuits. So here are the results. On the leftmost is the number of lookup tables. So blue is Chisel4ml and orange is Chisel4ml. And as you can see, Chisel4ml uses less circuits, especially for the low bit widths, and the generation time is drastically lower, like orders of magnitude. The downside is perhaps the pad delay, but that is kind of misleading because it can be easily mitigated because in Chisel4ml you get a combinational circuit, but then you can input like pipeline registers, and you can arbitrarily set the number of pipeline stages you want, and then you just use like register retiming in your synthesis tool to get desired pad delay. Okay, so thank you for your attention. You can check it out on GitHub. It doesn't have a lot of documentation, but soon.
Thanks, Jure. Questions for you? Go ahead.
Hi. Thank you for this very interesting presentation. I was wondering whether you were able or planning to actually run this on an actual FPGA?
No, but I see no reason why it shouldn't, because it synthesizes with Vivado, so it's just a matter of running the tools.
Okay. And did you encounter any timing issues in Vivado using this whole tool flow?
What exactly do you mean by timing?
I mean, when you synthesize the design, part of the reporting is timing analysis. It's done as part of a full compile in Vivado. So when you already said when you pointed to the option to infer registers. So if the path is too long, you would get a timing violation where there's too much logic in a chain.
Right.
So with this register setting, does it mean you basically never have any timing issues?
No, it doesn't mean that. What I was trying to say is, yes, you could easily get timing issues because it's a large combination circuit, essentially. But you can, there's a parameter you can set for number of pipeline stages. So this is just like basically it's a combinational circuit, so you can essentially, if you have a very low clock, you could, the initiation interval would be 1. But then you can put pipelines and synthesis, like use register timing in synthesis to kind of get higher clock rates, basically. So HLS does this automatically, but here it's up to the user.
Okay, thank you.
Yeah.
Any other questions? Well, go ahead.
For the result comparison with Chisel4ml, what model are you using here?
Sorry,
For the result comparison with Chisel4ml, what model did you use here?
What model?
Yes, what exact
So
model?
this is a model I train on the MNIST dataset. It's a convolutional neural network with 2 convolutional layers, I believe, some maximum pooling, and fully connected. In the
Okay.
paper, there's also results by layer. So actually, fully connected layers are pretty much equal, like in terms of quality of results. But for convolutional and max pooling layers, Chisel4ml does better.
Which version of H.S.4ml do you use? And did you use the IO parallel setting with data flow?
I'm using 1.0 plus some commits because,
Okay.
And then the mode is the delay.
Latency mode, and did you use the pragma data flow or pragma pipeline if you fully parallelize the model?
Yeah, I fully parallelized.
Yes,
so
is it data flow or pipeline? Because data flow with IO parallel convolution is known to be problematic.
I confirmed with the HLS4ML team that it is fully parallelized. So
Yeah, but did you use the data flow pragma? Because that is known to be problematic.
the data flow pragma, I didn't touch the pragma, so I
Okay,
used,
then it is.
yeah,
Then it is known to be problematic.
yeah. Okay.
And how did you measure the path delay? Because you have around 10 to the 6 lots, which won't fit in one chip. And how does the path delay only 2 nanoseconds?
So could you repeat the question?
You have around 1 million loops, which doesn't
Yeah.
fit in one FPGA. And how comes the path delay only 2 nanoseconds in this case?
Sorry, I am really having trouble.
So how did you measure the path delay? Is that post-implementation? So post-place and route?
Oh, this is from the Vivado synthesis reports. So
So it's a vSynth
it's
report.
not place and route reports, yeah. Just synthesis level reports.
Okay,
Okay.
so and you are reporting the maximum path delay.
Yes.
Okay.
Any other questions for you? This one. Oh. Go ahead.
So this is a general question that you will get now from me, basically, mostly because there is more time now, but it's a question that is about any kind of this approach where you use some tools that generate code, and then it's that code that goes through Vivado.
Okay.
So when I am at that point, say that that code doesn't do exactly what I want. I have a timing violation, or it doesn't go in the right place. I need to add max fan out. I had to add any constraint there. So I see a problem because people say, you go through this flow, but then there is a massaging happening.
Yeah.
And then my main problem is reproducibility, because maybe I have an algorithm in my board, and then in 5 years, people say, let's change that parameter. And I have to remember all the massaging bits. So what do you suggest we do? Which bits we should archive? Should we archive the source code? How do you suggest? It's a very general question.
Okay, regarding like reproducibility, it's, I think, much better than anything with high-level synthesis, just because, you can put it in a container and basically have it like that. Regarding the massaging, yeah, that's always the case, but here it's an open source, relatively simple tool, while HLS is closed source and kind of a black box, if you tried it. Yeah, I don't really have a better answer than that. It's always trickier than it looks.
That's still a good answer. And
Yeah.
like, if people have ideas about that, just come and talk to me, because this is my main problem now.
Yes, but if you use open source, you can have containers and then kind of have like CI and stuff like that.
So you are suggesting to maintain a container with the specific version of your tool so that you can always run the CI there, even in 10 years when...
I guess.
Yeah, that was my
But it's
idea
also
as well.
kind of computationally expensive, so.
Questions? Oh, David.
So I guess in your test you were just using AMD devices, no? But I was curious if the Verilog code that you generate does contain some primitives, so it's pure RTL that you can in principle implement in any FPGA.
Yeah, I mean, I can show it quickly. I guess not, no, because the sharing mode is not correct. So it's completely generic, and also this is based on the circuit framework that has like modes that you can like work around bugs in Vivado, and you have like special mission modes that you can, you know, if your tool doesn't support like some feature of system Verilog, you can set, please don't emit that feature. And so it's kind of controllable in that way. Yeah, so it is generic, yeah.
So I also have a question based on the names. You say you're using the Chisel language. What is the benefit using that compared to, I mean, Verilog or system Verilog?
Sorry?
What is the benefit using Chisel
So,
compared to other?
Chisel is kind of conducive to writing reusable generators. So to do this in Verilog, it would be basically impossible. You would have to use like some Python or something to generate the Verilog. But here you have like a type-safe metaprogramming environment. So it's easier in that way.
Any other questions or comments? If not, let's thank the Jure again for the very nice demo. And we can move on to Jožef.